Okay, hey everybody. Hopefully this is working here. And yeah, so I guess let's get started here. And I'm going to do a couple things first. Sorry, I closed it there for a minute. So yeah, this is just a chance to ask questions. So I know the school year has started for quite a few people, and maybe not you just yet, but if it has, maybe you're a little rusty, feel free to ask anything. And if no one really has questions, then I'm happy to just bounce. So, yeah, hey, Miss Stacy, I saw you there. Eli, thank you. You're also nice. So, Captain Chaos, I guess let me address your question first, since you asked first. So, you're taking physics with Calc 1, right? So, physics with Calc 1. So, I only took one physics class. I took one in high school, don't even count it. And then um, I will answer that, Ms. Stacy. That's just a notation question. That'll be easy. So yeah, it's just notation. But Captain Chaos. So there's really a lot going on. I mean, the main thing is, so a lot of the applications that you'll want to do in physics, you can't really do those applications without calculus, kind of the interesting things. So kind of calculus is sort of it's sort of a toolkit to do cool stuff. It's kind of the idea. So that gives you sort of the mathematics to work with. And typically what you'll see is, I assume the way that you'll see it, it'll probably start off pretty normal. You'll probably see limits first. That's typically how calculus courses, every calculus course I've ever taught starts with limits. Now, there's kind of a trend right now for that not to be the case, but I would assume, especially for a physics course, that you would see limits first. And the idea is you need the notion of a limit because limits tie into derivatives. And derivatives, what they do is somehow they quantify rates of change. So the idea is maybe I have, for example, and again, maybe this is going to seem a little vague. I hope not. I'm trying to give a very quick little intro as to what you might see. So suppose you have something that tells you, suppose the x-axis represents time and the y-axis represents the distance you've traveled. So maybe you're a jogger and you're running away, you're going away from home, right? So maybe at time t equals 0, you're at home, and then as time elapses, right, you go further and further away from home. And okay, so during that time, right, if you look at that graph, you would think, well, just based on the time and the distance away from home, you're kind of moving a little faster at certain points of time compared to others. And there's an interesting way, so only if I know, for example, about the distance away, what we can actually do is manipulate, if we have a formula or a graph, is we can start manipulating that information, and you can now start answering information about, you can talk about what your instantaneous velocity is, or you can talk about what your acceleration is. So the idea is by knowing one little bit of information, you can actually extrapolate a lot of other different pieces of information. That's going to kind of be the hand-wavy, I think, way they're going to present this stuff in your physics course, because they're going to want to introduce these math concepts, but again, in a physics setting, so that you're trying to kill two birds with one stone. And again, that's probably like a 2-minute introduction, what you're going to do. What the heck are limits? What the heck are derivatives? Well, we didn't really address that question necessarily, other than just with a couple examples. So to compute a derivative, you have to use the mechanics of a limit. So you have to understand how to compute these things called limits. And there's just a process involved. And of course, there's a conceptual understanding of it as well. That gets you to derivatives, and then you understand derivatives, and there's just a lot of mechanics in taking derivatives is the idea. Okay, So let's, I don't know if that helps at all. Sorry, I'm reading some of the comments here. Some geo, I'm missing? Intermediate, some geo, like geology or geography? I don't even know what geo is. Um, Sine x squared is the same as sine squared x, but why? Why does the sine square but not the x? So Miss Stacy, this is just a notation question. Oh my God, excuse me. Geometry. Okay, that makes much more sense, doesn't it? Thanks. I realized I was missing the forest for the trees. I have never taught geometry. I actually don't have many geometry videos on here. I thought about making some. I don't even know. I probably should. Anyways, it's just a notation question. So you're saying, yeah, it's just as Math Teach said, it's just another way of writing it. So we want to talk about, sine of x quantity squared. That's what we're talking about. And sort of the way is there a different notation in writing that? And at some point, someone decided, hey, let's write this as sine squared of x. And then it's just understood that when we write sine squared of x, what we mean is, we mean that, right? We mean this. And in this case, if we write sine of x squared, like we have on the right, well, it's understood that means sine of, now the only thing being squared is the x. So again, it's not really an understanding question, I think, so much as like an understanding the notation, just understanding the language. And I remember for a long time, too, when I first started taking trig, I was like, what is this? Sine squared of x, well, what are we talking about? And then somebody said, hey, dude, we just mean that. And I said, oh, okay. And then I was fine with it. Mystery solved. So it's just a notation. It's like, how do you mean sine of x times sine of x? Or how do you mean sine of x times x? How do we want to write that? And this is just how we write it. So that's it. Yeah, so here it's understood, right? When we write sine of x squared, the only thing being squared is the x. So I even tell people, maybe it helps to really put that in parentheses just to really emphasize in your mind that it's not sine of x times sine of x, right? It's just sine of x times x. So I hope that answers it. So sine is fundamentally different than other things multiplied by x. No, sine is absolutely not different than anything else, Miss Stacy. It's absolutely not different. Yeah, so maybe you can ask that question again, Miss Stacy, if you want to elaborate on it. Because yeah, there is nothing fundamentally different about sine at all. And you're asking, so you said, why is sine of x squared the same thing as sine squared of x? Did you ask this? Okay, sorry. Sine of x squared is the same, but why? But why? Because we all agreed that by writing sine squared of x, we mean sine of x squared. That's it. That's the only reason why they're equal. That's just what the notation means. You know, when mathematicians were creating this notation, they said, hey, when we write this sine squared of x, what I really mean is this. And everybody said, okie dokie, and that's it. There's no reason beyond that. That's just how we write it. Yeah, exactly. So sine is not separate than x, right? So sine by itself, this means nothing. You know, just writing sine, that doesn't mean anything, right? Like they're two different things. Sine means nothing. Sine of x means something. That now has a meaning. That now means something. You're taking x and you're putting it inside of sine. It's like the same thing. It's just like saying square root. Square root doesn't mean anything by itself. I mean, there's this notion of what a square root is, but in terms of like producing something, if I just say square root, right? Just square root doesn't do anything. The square root of 4, okay, that does something, right? I'm performing an operation now. So in this case, just like, you know, square root, that means nothing. It doesn't do anything. But the square root of x, aha, that means something. It means take that number and figure out what multiplied by itself equals that. No, there's nothing, there's nothing different about an x inside of a sine function. No, there's nothing at all. You know, just like to me when it says sine of x, to me what this says is find, all this means to me, it says find where the angle x hits the unit circle, and then it says what is that y value. That is the number that sine of x is going to return. Sine doesn't mean anything because you need to input something. Just like the square root doesn't mean anything, right? But the square root of x, it says, we know what the square root of x is. What number, and we use positive numbers, what positive number, let's write it out. You know, what positive number multiplied by itself equals x. So they just mean, you know, there's nothing different about square root. It's just a symbol. There's nothing different about sin. You know, instead of writing a little square root, for some reason we use these 3 letters instead. You know, instead of the square root, we use sin. But they mean different things, right? The square root, we know what that means. What does sine mean? Well, it means this. So that's all it is. But they mean different things, but there's nothing fundamentally different about the rules. And that's something you should be careful about, because if you ever, and this is a good question, Miss Stacy, you're a good point. If you ever think like there isn't an exception to the rule, for some reason, I think just like you're doing, like that's almost a good indication that maybe something's wrong, right? Whenever I did that, I was like, oh, this doesn't fit the mold. Usually I was like, okay, I'm missing something because there's no reason. Like everything should be consistent, right? Usually, everything, well, not usually, it should be. Everything should fit together. And if something doesn't fit together, that to me told me that I'm usually messing up because it should fit in just like everything else. Let me read through these questions again, just a little bit. Okay, does that work? Okay, perfect. All right. Oh no, I'm running out of space. I've got so much stuff on my poor iPad. I think I can keep writing though. It should be okay. Yeah, so again, you know, we could use some different symbol besides sine. You know, it could be, you know, we've got that little square root. Maybe we can make a different weird little square root symbol, right? That means sine of x. Well, it means whatever we want it to mean. We don't write that though. Again, right? We just write sine. And cosine is the same thing. It just means we do the x value instead of the, well, we should be careful. But you don't want to think about the input as the x coordinate. So just, I'll be careful there. Okay. Excellent. All right. Hey, if that works, then I'm going to shut up. But please ask questions. And I know especially too, like communicating just via text is super hard to do. It's not an easy, I mean, gosh, it would be so much easier, right, if we were like sitting next to each other. So that's one of the limitations about doing it this way. But it is what it is. So, okay, I don't know. And if people don't have questions, will sit here and turn my camera off and just kind of hang out. Whoops. I'm going to hang out in the background and just lurk. And if people have questions, I will be happy to jump in. And if not, like I said, this is kind of an experiment. This is just kind of an experiment, the little office hours. And it's new. I think maybe as people, if I do it consistently, I think more people will come. But we'll see. So I'm just going to write that. Feel free to post. Feel free to post questions. I'm lurking. I probably won't do proofs at the moment just because I'm mentally not really prepared. And honestly, I think a lot of people, I guess it depends on what kind of proofs. I don't even have a good geometry book to use. I would have to go dig one out. If you're talking about geometry proofs, I would love to at some point, but probably not this moment. That's actually something I would like to do, if that's what you mean. It's been honestly a long time since I've done them. Probably since high school. Or go over the different factoring methods. Yeah, so we could look at factoring. We could certainly go over some of that in terms of the algebra stuff. That's certainly not a problem. I guess you're talking about, yeah, don't be sorry, of course. So like a little bit on factoring. And there's a lot really to know. Well, I mean, there is and there isn't. So I guess a couple quick things to remember about, yeah, but that's okay. I mean, I have to teach it. The first time I taught calculus, I didn't remember it. You know, every class, it was the night before, spending a few hours going over it. But at that point, I was really well equipped to understand it. You know what I mean? Like, it wasn't like I was learning it the first time. I was like, oh yeah, I got this. But I needed I needed that. So I know there's the box method, the vertical method. Yeah, I know they're called that. I don't even know how to do those. It's all foiling. Let's talk about a couple real quick. The box method does this, I remember. I never learned it this way as a student, and I never taught it this way in college. So if we're talking about factoring polynomials, and that's what I guess I'm going to restrict myself here to real quick because that's what the box method refers to. So polynomial, remember, is you've got something of the form a to the n, x to the n, plus a to the n minus 1, x to the n minus 1. And I'll give a couple examples here, plus some constant. And we don't want the leading coefficient to be 0. So a couple examples. So y equals x squared minus x minus 6. That would be an example of a polynomial. Sure, you can ask about your math doubts here. I don't know that I will be able to clear them up, but it's always often leads to an interesting discussion. So that would be an example of a polynomial. Y equals pi times x to the 100th minus the square root of 8, x to the 4th minus x. That would be another polynomial. An example of something that wouldn't be a polynomial, though, would be if we have like fractional exponents, minus 4x plus 8. So that would mess things up, and this would not be a polynomial. So what you're looking for are exponents that are positive whole numbers, or you could just have constants floating around. We don't care about the coefficients. Notice in my second example, I've got a pi as a coefficient and the square root of 8 as a coefficient. So that's fine. Now, the question is, so again, we're skipping the last one because that's not a polynomial. But in general, what we want to do, the goal is we want to take our polynomial, we want to set it equal to 0, and we want to be able to solve it. That's the goal. And this sounds like such an innocuous little goal. You know, it's really not doing it justice in the cosmic scheme of things, right? There's only 18 people here, and we're talking about one of the most sort of important questions of math in the past minute about solving. Figuring out how to take a polynomial, set it equal to 0, and solve it, that has been a difficult question for a long time, and there were a lot of open questions surrounding that. And historically, it's very interesting. But that's the goal. How do we do it? And typically, the way that we do it, to do this, we typically try to factor. That's the main thing that we try to do, if we can. There's other ways to do it. We can use, you can sort of do it by trial and error. You can use the quadratic formula if it's a quadratic. You can use the rational roots test to try to find potential roots. But for example, if somebody gave me this question, the second one, and said, hey Patrick, take this polynomial and set it equal to 0, I would say, okay, I know one answer right off the bat, right? I know one answer right off the bat, but finding the others would be more tricky. So in general, this is a hard question. Okay, so let's talk about factoring real quick. And the ones you really need to factor are quadratics. And then, okay, so the first thing we need to solve are, we need to be able to solve linear equations because that's what they all turn into, right? If I have like x minus 2 equals 0, to solve that linear equation, I could simply add 2 to both sides, and it says, hey, 2 is my solution. And feel free to make comments or questions or whatever as I go through this because I'm trying to glance. So 2 is a solution to this equation. If I put 2 on the left side, I get 0 out. Now, to solve a quadratic, for example, like we had x squared minus x minus 6, suppose I set that equal to 0 and try to solve that. Now, this is the thing. With a lot of, eventually you want to solve a lot of different types of equations. And it's just one of those things like, if it's this type of equation, well, you do this. If it's this type of equation, well, you do this. And how do you do this? Well, there's all the algebra involved. And part of that is just, you know, something that, it's just part of math, sort of having that skill set to be able to do that with different types of equations. A quadratic is one of the most fundamental, though. So notice, right, my right side of my equation is equal to 0. You always want that. Do not do this if the right side, if one side of the equation is not equal to 0. So this is a special case. And I think this is where they do that whole box method, right? I forget exactly what they do. I could look it up, but so this is the special case, and the reason why it's a special case is because the coefficient on the x squared is just a positive 1. So in this case, we look for two numbers, right? Look for two numbers that multiply to -6. So if this special case is satisfied, you look for two numbers that multiply to the constant that add up to whatever the coefficient on x is, which in this case is a -1. So can I think of two numbers that multiply to -6 but add up to -1? Well, I think if I use, what could I use? How about +2 and -3? I think those two numbers would fit the bill, right? If I multiply those, I'll get -6, but if I add them, I get -1. And that tells me how to factor, because now this says we'll have x minus 2, and then x plus 2. I'm looking at something else here. So we take each of these numbers, and oh my gosh, there we go. Okay, and I'm just going to drop those two numbers in. So I have x plus 2 and x minus 3, and this is still going to be equal to 0. So notice I just used those two numbers, positive 2 and negative 3. And you can distribute all of this out to make sure you get things back. Now the idea is, right, once we have each of these factored, it just goes back to the linear case. We just take each one of these and set it equal to 0 and solve. So for the first equation, I could subtract 2 from both sides, and from the second one, I could add 3 to both sides. And those would be my two solutions. And recall that finding solutions, this is also something that's important. If you go to graph it, by taking any expression and setting it equal to 0, if you go and graph that, what you're doing is, recall that these are going to correspond to x-intercepts. So taking an equation, setting it equal to 0 is equivalent to finding x-intercepts. So I now know where those x-intercepts are. So the idea is, if I were to graph y equals x squared minus x minus 6, so there's x squared minus x minus 6. If I go to graph that, I've already found 2 points, at negative 2 and at 3. So okay, that's how we bring, you're trying to break quadratics down into linears. That's the idea. If you don't do that, to solve it, I would just use the quadratic formula. And for example, suppose somebody said factor this. So we had x squared minus x minus 6. Factor slash solve. We had this equation that we were just doing. Well, what if I just erase that minus 6, and what if I were to make it into let's make it into, how about a minus 7? Now it's like, have fun. How does this factor? X and x gives me x squared, but give me two numbers that multiply to negative 7 but add up to negative 1. And if you can't think of any, I can't think of any either, because there's not two nice whole numbers. But you could solve this using the quadratic formula. And the same thing, what if it was x squared minus x minus 6 equals 0, but instead of x squared, what if I had 2x squared? Well, if that coefficient is not just a 1, if the coefficient is not just a 1, that trick of finding two numbers that multiply to negative 6 and add up to 2 no longer works. So what do? Well, again, I would use the quadratic formula. Well, what if you had something like this? And I see your question there, Alexander. I think we can do that one here in a second. Examine the flow. I've never heard it called that. You'll have to help me with what flow means. We'll just graph it, though. And tell me if you're in calculus or not, because I would certainly want to use calculus to do that. But we can come up with some good stuff without calculus. Suppose we had something, so we had x squared minus x minus 6 a second ago. What if I bump all those up? X to the third minus x squared minus, let's say equals, how about we make it equals 6x? Well, the first thing I would recognize is it's a polynomial. I should set that equal to 0, and I'll do that by subtracting 6x from both sides. And then I would think, well, is there anything I can factor out? Well, you could factor out an x. And again, notice now I'm back to my last problem. I would take the first term, the first factor and set it equal to 0. And then I would take that second factor and set it equal to 0. But we now know how to factor that. So you see what I'm saying? You're just trying to break things down, break things down, break things down, break things down is what you're trying to do. So that would be my quick little 5-minute sermon on factoring. What is the box method? Like, they want an x squared. How do they write it? So like x and x gives you x squared, and you want that. And then you just use those two numbers. What is it? You do like -2, so that's going to be -2x, and then I guess we put a 3 here, so that's going to be 3x, and then that's going to be -6. So I think that's the box method. You're sort of looking for, it does something like this. You're looking for these two numbers, which is exactly what we did here. Because -2x and 3x, hey, if you combine those, whoops, I got those backwards again. I keep writing the roots. That looks better. Because if we add those, we get -x, and if you multiply them, you get -6. So I think that's something, I think the box method basically does something like that. I never liked it because to me it was just overkill. I would rather just write down a couple numbers and be off and running. But I know this box method is taught pretty heavily, and you know, whatever works. Yeah, I'm just trying to learn method to teach my kiddos. Okay, that's great. That's super useful. So I found both methods work with kids. I've definitely done the box method in the past because I remember people, you know, I have had younger kids every once in a while that do it. And I'm like, oh yeah. But typically, it's one of those things, right? If you're working with some kid, it depends on who you're working with. Some people need it and feel more comfortable with it. It feels more structured. For me, it just felt like unnecessary tedium that added clutter that I didn't like. So, you know, it's whatever. You tailor it, hopefully, to whoever you're talking to. So, which obviously you've got under control. What are some things I should know pretty well before taking DE? So, Alexander, you erased your question, so I've lost your question. I think it was what, like x to the third over x plus 1 squared or something like that. Diamond method, and that's another one I don't remember. I'll have to look at. Yeah, it kind of depends on what you're doing in differential equations. I kind of told people differential equations really kind of felt like calculus 4 is really what it was. I mean, right? A differential equation is just any equation involving a derivative. Y equals x squared. Well, the derivative y prime equals 2x. This is a differential equation. So you've been really dealing with differential equations all through calculus. All through calculus. It's just now you're going to start doing, you're going to start focusing, okay, I think I had it right. You're going to start focusing more on techniques to solve some complicated differential equations. You're going to start interpreting them more, and you're really just going to start thinking about using them more. So I would say some things you should know pretty well before taking DE. The one things I would say, just at a glance, before DE, certainly some linear algebra. I remember I took differential equations having never had linear algebra, so that does depend on your class. So before DE, I would just want to remember, really, you don't even really need to remember multivariable calculus. So I would remember Calc 1 and 2 stuff. And by Calc 1 and Calc 2 stuff, I would just say know how to take derivatives. It's going to sound like very basic, but it's the truth. Be able to take derivatives forwards and backwards. And the harder thing is be able to find antiderivatives or integrate. Because there's going to be a ton of that. Right? If you don't remember that 1 over 1 plus, if you don't remember how to integrate, say this, if you don't remember how to integrate, say, 1 over 4 plus x squared dx, I would say you might need to review. Derivatives, most people don't have issues with. Derivatives are easy, and I say that not to be like, oh, geez, they're easy. They're easy in the sense that they're mechanical. There's a process. When I look at a function, and somebody says, hey, take the derivative, there's no guesswork on how to do that to me. I'm just like, boom, this is the procedure. And I've done enough of them to feel comfortable with the procedures. When it comes to integration, though, that's like all out the window. I'm like, ugh. This could be one of like 5 things, and if it's a little different, you use something else. So you're going to need to be really handy with integration. Hopefully you took like a Calc 2 course pretty recently before a differential equations course. If not, remember that. When I've tutored people in differential equations, typically that's what kills people. The other thing in differential equations, a lot of the questions are going to be word problems. They're going to be applied questions. So they are going to be more sort of understanding based, which makes it more useful but more complicated. Okay, Alexander, you are very patient. Let me look at this. Okay, so this is like one of those curve sketching ones, right? You probably, and let me know if let me know if any of this is making sense or helping too. So, yeah, integrals are just hard, you know, and honestly, it's been a while since I've done some of it. I used to be, at some point I could have written a calculus book, and I could probably still write about 85% of one. But yeah, I forget it too, so it's okay. Yeah, good luck with DE. Like I said, it really feels like a Calc 4, or it feels like a much more sophisticated continuation of like, for me, it would have been a Calc 2 class. Whatever, after you've seen integration, especially make sure, the other thing I would say, make sure you remember series. Because you will absolutely see series when you do differential equations. So make sure you remember series expansions, and that's something that gives a lot of people issues. Okay, Alexander, once again, thanks for your patience. These questions have a lot of parts, right? So you tell me how much we need to do on this, because they usually ask about the domain. The range is harder. We'll talk about horizontal. We'll talk about asymptotes. We could talk about asymptotes. You could talk about where it's increasing and decreasing. You can talk about concavity, inflection points, local max mins. Do you want to see all of this stuff, Mr. Alexander? I don't know why I'm pronouncing your name that way. I saw such a funny video this morning. Made me laugh. The guy was pronouncing things very funny. Domain, intercepts, monotonicity, stationary points. What are stationary points? Those are like where the derivative is 0, right? Inflection points. Okay, you want to do most of the stuff. Okay, let's go through this. So this will be a good review for those of you doing calculus. So this is all a big calculus question. Okay. So this is basically a big calc question. Okay, so buckle up because you need to learn all of this. Okay, well, buckle up, it's going to take a few minutes. These questions are typically kind of long, but it's good. And again, for those of you maybe just even taking algebra, the beginning part of this will be algebraic. There's no calculus involved. So a lot of this you'll still be able to follow. And this, I guess, is a good point where I'm supposed to take a little segue. Don't forget you can head over to Patreon. And you can support your friend, Patrick JMT, for as little as $1 a month. Okay, let's do this. Let's talk about domain first. So how would we find the domain of this function? And to me, the domain, really, I'm looking for 2 things when it comes to the domain. I want to exclude values of x. I want to exclude values of x that either produce 0 in the denominator of a fraction or that give me a negative number underneath an even-powered root. Now, I just wrote a square root, but an even-powered root is what I mean. I'll even put under there, even-powered root. You just typically will see a square root, though, in a calculus class. You're not going to see too many 10th roots, I think. Okay. Now, if I go back to this lovely function we started with, I think, does any of that apply? Does any of that apply? Well, there's no square roots even floating around, right? There's no square roots even floating around, so I don't have to worry about that restriction. The other thing I would think about is there anything that would make the denominator equal to 0? So are there any solutions to, and I'm asking this as a question, I just take whatever's in the denominator and set it equal to 0. Are there any solutions to that equation? And if there are, that's bad. I need to throw it out. Well, I can take the square root of both sides. And again, this is where, depending on what's in the denominator, it's what we said a second ago. You're taking some type of equation and setting it equal to 0. How you solve that, it just depends on the equation that's chilling out in the denominator. This is just going to be a quadratic, so it's not too bad. I could take the square root of both sides, and that would just give me x plus 1 equals 0. Well, I could subtract 1 from both sides, and that would give me x equals negative 1. So again, this is bad because it makes the denominator equal to 0. So my domain is going to be everything except for that number. Negative 1, I'm going to put a big open circle there, but then everything else is good to go. So here's negative infinity, here's positive infinity. So my domain would be from negative infinity up to negative 1. We write a little u or a union sign. It's not a u, it's a union sign. Negative 1 to infinity. Recall we use the parentheses because we skip over that value. Okay. Can I explain how to use the second derivative test to find maximums? Yeah, we can do it even in this problem. So I never use the second derivative test to find maximums unless it's in a multivariable course, then you have to. But I wouldn't do it in the first semester. It's not necessary. Okay. So that's the domain. Intercept. So let's do x and y intercepts. So to find the x-intercept, right, we simply let y equal 0 and solve. So that's going to be a little tricky. That's the harder one. And to find the y-intercept, we let x equals 0, and I'm not going to write solve, I'm going to write and compute. So let me copy and paste this because we keep using this. Copy, paste. Okay, so I'm going to do the second part first just because it's easier. So if I plug in 0, well, f of 0, that's just going to be 0 to the third over 0 plus 1 squared. That's going to be 0 over 1 or just 0. So that says if we plug 0 in, we get 0 out, which really should already tell you what at least one of the x-intercepts is because we just found it. The other thing we would do is we would take so to find the x-intercept, we would take whatever we started with, and we would set that equal to 0. We would take that and set it equal to 0. Well, again, you can think about it in two different ways. The only way for a fraction to equal 0 is if the numerator is equal to 0. Well, the only thing that's going to make the numerator equal to 0 is if we plug in x equals 0. That's one way to do it. Another way to think about it sort of algebraically, just sort of mechanically, is what we're doing is, to solve it, you could multiply both sides by x plus 1 squared. Well, that's now going to leave you with just x to the third equals 0. And if you take the cube root of both sides, well, you still get x equals 0. So that would be so the x and y intercept, it just goes through the origin, is the only place where this graph crosses the That's the only place where it crosses the x-axis. Okay. So that is, let's see, x and y intercepts, and then it really comes into, let's talk about asymptotes too. Oh my gosh, this is such a long problem. So let's see, vertical asymptotes. To find vertical asymptotes is relatively easy. This is easy if you have a rational function. And a rational function is just a polynomial over a polynomial, which is what we have in this case. So x to the third over x plus 1 quantity squared is a rational function. And in a calculus course, they usually, a lot of times when they give you these curve sketching ones, they like to give you rational functions. If you'll also see some with trig, but they're like these. Okay. So we've got our rational function here. So vertical asymptotes occur at values of x that produce something non-zero over 0. So if you can find a value of x that makes the denominator equal to 0, but the numerator not 0, what part of Indiana? Hey, Brian. You Hoosier. You're my rival, so I gotta call you Hoosier in a mean way. But I still like you. So if you're trying to find a vertical asymptote, yeah, you're looking for any value of x that. Okay, you're revealing your age there, but you're in good company, so that's awesome. Yeah, thanks. Evansville, okay. I know exactly where Evansville is. So, isn't Evansville directly across from Louisville? Isn't that Evansville? That's Evansville, yeah. Am I crazy? So, okay, so that's what we're looking for. So in this case, it's easy to do because if you look at x to the third over x plus 1 squared, we've already done this. We see that at x equals -1, that satisfies this condition, right? This is going to give you -1 to the third if you plug it in. It's going to give you 0 in the denominator if we plug it into our original. Yeah, okay, I thought you were pretty close. Okay. So notice if you plug -1 in, it makes the numerator not 0, but it makes the denominator equal to 0. So already I know at -1, I'm going to have this vertical asymptote. So now I know a little bit more about my graph. So to find horizontal asymptotes occur if one of two things happen. If the degree of the numerator equals the degree of the denominator, or if the degree of the numerator is less than the degree of the denominator. So that's when we have horizontal asymptotes. And Alexander, are you still out there? Are you with me? I just want to make sure. Y'all feel free to ask questions. So we're doing some calculus stuff for anybody that's joined, a curve sketching problem. And I will say, Alexander, I've got quite a few of these at least buried somewhere. So if the degree of the numerator is equal to the degree of the denominator, we've got a horizontal asymptote. And to find that, you can take the ratio of the leading coefficients. That's kind of the shortcut way. To do it, we're going to take a limit, is what we'll do. And if the degree of the numerator is less than the degree of the denominator, y equals 0 will be a horizontal asymptote. Yes, find them with limits, so let's do that. Okay. So we could justify, for example, so let's justify. So I just claimed that using this little procedure, finding something non-zero over 0 that's going to give you a vertical asymptote, let's justify that. Let's justify that x equals -1 is a vertical asymptote. Well, to do that, we have to show really one of four things. And I'm not going to write it all out just yet. But we would have to show the limit as x approaches -1. So I'm not done with my limit here yet. I'm going to add some stuff on. We would have to show the limit as x approaches -1 of our function, x to the third over x plus 1 quantity squared. We have to show that this equals, now a couple things. We can show one of four things. So I could look at the limit as x approaches -1 from the right. And if I can show that that equals positive or negative infinity, that means that -1 is a vertical asymptote. Likewise, instead of approaching -1 from the right, we could come from the left. And again, that means if I get that, I've got a vertical asymptote. So in terms of the graph, all we're showing is, suppose I approach -1 from the left. So here comes in my graph. Here comes my function. And you can kind of think about that vertical asymptote as like a wall. Now my graph could just stop and say, boop, I'm done. And then it's not a vertical asymptote. Or that wouldn't mean it's a vertical. It wouldn't be a vertical asymptote. It's just undefined is all it is. But for this type of function, what's going to happen is it's either going to spike up to infinity or it's going to spike down to infinity. And the same thing's going to happen on the other side of the graph. If I approach from the right, it's either going to go up to infinity or it's going to go down to infinity. And it should cross through that intercept. So one of those things are going to happen in terms of the graph. And I'm just trying to show that. So I don't know. Do you want to take -1 from the left or -1 from the right? I don't know. I'm going to pick -1 from the right. So I'm going to use the limit as x approaches. Any of them will work, is my point. So I would just say something like, notice, well, as x approaches -1 from the right, x to the third is going to get close to what number? If you take a number close to -1 and you raise it to the third power, well, it's still going to get close to -1. And as x approaches -1 from the right, well, x plus 1 quantity squared, well, that inside is going to get really close to 0. Right? If I plug in something close to -1, and if I square it, this is going to get really close to 0. It's going to be close to 0, though, but positive. So I could say, and I shouldn't write equal sign, that's bad, that's incorrect notation. I should say that this approaches 0 as well from the right. And therefore, I could just conclude that limit as x approaches -1 from the right of x to the third over x plus 1 squared, that's going to equal -infinity. That's what it tells me. I've got something getting close to a -1 in the numerator, and it's getting close to 0 but positive in the denominator. So it tells me as I approach -1 from the right, in fact, my graph should be doing that. It should be going down. And you could actually justify that it does the same thing from the left as well. Okay. And I know my graph doesn't cross the x-axis over here because I would have found another x-intercept. So my graph has to stay sort of in that bottom left quadrant. Okay, we're having fun, lots of stuff here. So I guess let me stop there. Does that make sense for the vertical asymptote? Okay, so notice in this case, though, there is a slant asymptote if the degree of the numerator is exactly one larger than the degree of the denominator, than the degree of the denominator, which is exactly what's happening in this this case. There is a slant asymptote, because notice in the numerator we have x to the third. If you square out the denominator, you're going to get x squared plus some other stuff. You're going to get a slant asymptote. And really what we're looking at, though, to figure that out is we're looking at end behavior. And to figure out end behavior, what we're going to do is we're going to look at the limit as x goes to negative infinity of that function. And we're going to look at the limit as x approaches positive infinity of that function. So I guess the question is, have you seen ways to evaluate these limits? Hey, hey Sarah, I'm glad you did well in high school. Thanks for the kind words. Hey Gav, so let's see. So the idea is to, so you could take limits. So to compute these limits, you could use L'Hopital's rule, if you've seen L'Hopital's rule, to compute these limits. Another way you can do this is just to find the asymptotes, you can do long division. So I don't know if I need to do this all the way out. I would prefer not to. So the denominator is really going to be x squared plus x plus 1. So you could do long division if you remember how to do polynomial long division. And then you could rewrite this function. It's going to be x plus some stuff, which is going to be the remainder. But the idea is if you take the limit as x goes to negative infinity, all of this part is going to go to 0, whether you go to positive or negative infinity. So really, you're going to get a slant asymptote. You're going to get a slant asymptote of just the line y equals x, is what you should be getting in this case, I think, unless my math is off. That should certainly be right. So, okay, I found a vertical asymptote. It turns out we're going to have a slant asymptote as well. So, and then there's my other slant asymptote. Okay, so I'm getting some more information about my graph here. So let me try to fill that in a little bit. So already I know I've got a vertical asymptote here, but if this is going to be a slant asymptote, my function has to start hugging it over here. Now, there was only one, it went through the origin, but again, it's an asymptote here, and it's got to cross, but it's got to get closer to this line, so I don't know, maybe it does something like that. Anything can happen here, is the idea. Use L'Hopital's rule. Okay, L'Hopital's rule is easy. Let's do one. So if we use L'Hopital's rule, because right now, let's do the positive infinity one because that's easier. That's going to be infinity over infinity, which is indeterminate. So we can use L'Hopital's rule. It's valid to use that. So I'm going to put a little LH for L'Hopital's rule. That's going to be the limit as x goes to infinity. This is going to be 3x squared in the numerator. The denominator, we would have to use the chain rule. We would have 2 times x plus 1 to the first times the derivative of the inside, which is just times 1. But again, notice this is still going to be infinity over infinity. So I could use L'Hopital's rule again. This is going to be the limit as x goes to infinity. I would get 6x over, notice in the denominator, if you distribute, you would get 2x plus 2. That derivative is just going to be a 2 in the bottom. This is clearly going to go to infinity, which again means as x goes to positive infinity, as you go to the right, it says that your graph should be going up towards infinity, which is exactly what we have happening over there. So what should happen, you should be able to show, and I'll leave this to you, where did it go? You should be able to show that this other one should equal negative infinity. So there's going to be a few steps in there. You should really end up with the same thing here. The only thing that's going to change is you'll have a negative infinity down there. And that should equal negative infinity. So that means if you go to the right, you're going down on the graph. Alrighty. So that is the end behavior, which also helps me figure out, by doing long division, that's how I would find the slant asymptote. Okay. Let's get into the calculus-y bits. I guess we're already doing calculus. Well, technically, with the limits, we were doing calculus, but with the long division, we were just doing algebra. So again, you could have gotten everything I've gotten so far, almost just with algebra. I'm doing a class here in Michigan that is proof-based, linear algebra. Yeah, almost any linear algebra course is going to be proof-based. Could you go over some basics? Yes, eventually. Probably now is not the time because I've already an hour into it, and that is certainly something more intense. But yes, and I do have some basic linear algebra proofs and some stuff. But yeah, I think linear algebra is a shock to the system for a lot of people because that is the first time that they tend to see linear algebra proofs. I know one of the strongest people I know in linear algebra. Maybe I can convince that person to come and to do a review. What if you use, let's see, this is blocked out, kx plus n for the slanted asymptote? Yeah, it should be a line. That would be the slant asymptote. Does it just come out to be y equals x? Is that what it is? We could do the long division. I'm going to leave it to you. It feels like it should be x. I guess you could easily get a number. Let's do it. I'm going to do the long division real quick, just because now I'm concerned. Let's do the long division. So we've got x to the third divided by x squared plus x plus 1. Let's do it. X squared plus x plus 1. I'm going to fill in some placeholders because I like to do that. So let's see. I think x squared times what is x to the third? Well, I'm going to need an x. And then I distribute that to everything. So x times x squared is x to the third. X times x is going to be 1x squared, and x times positive 1 is going to be positive x. Yeah, and then you subtract everything. So if we subtract everything, the x to the thirds cancel. We get a negative x squared. It looks like a minus x to me. And now I can do this one more time. So I think x squared multiplied by what is negative x squared. And so it looks like my asymptote was incorrect. I should be careful. So it looks like x squared multiplied by negative 1. That's going to give me negative x squared minus x minus 1. And at this point, you're just going to end up getting some extra stuff. I don't care about this part. This part that looks like a line, this is going to be your asymptote, y equals x minus 1. That's going to be your slant asymptote. So I put it as y equals x just because I kind of assumed that's what it was, but it's definitely not that. Assuming my long division was correct there. So what do we say? X minus 1? I've already forgotten. X minus 1. That's going to be our slant asymptote. Which is fine. I just need to make my graph hug those a little better. So my graph still basically works. I just need to. So really to get that slant asymptote, just do the long division better. I was being a little sloppy. I didn't do it all the way out. What will you get? Just looks like you'll just end up with a plus 1 here, which is going to be your remainder. So you would have plus 1 over what you divided by. So that would be the long division for, that would be a way to rewrite x squared, or excuse me, x to the third over x plus 1 quantity squared. It says we can write that as x minus 1 plus 1 over x plus 1 quantity squared. That's what we're doing. We're just doing an algebraic rewriting. And this is the interesting part because as the limit as x approaches positive infinity or negative infinity, again, this term is clearly going to approach 0. And you're just going to basically be left with the x minus 1 portion. It says that part will still be there, which is why that gives you the asymptote. So let me know if that makes sense. And I'll probably do this last part. Maybe we'll call it a day here, because this is still going to take quite a bit. Are we okay for the moment? Let's do some derivatives, and then we'll see what happens. Can you go over the principles of topology? Probably not at the moment. Yeah, I think that's a little too heavy. So, okay. So let's talk about first derivatives and second derivatives here. So here we're going to have to use the quotient rule. So it says if you take the derivative of a fraction, it says you get the bottom one times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So this is where it's going to turn into one step of calculus, and then it's going to turn into a whole lot of algebra. So let's do our quotient rule. So it says we get what's in the denominator, which is just x plus 1 quantity squared. We take the derivative of the numerator, which is 3x squared, minus the numerator, so we'll leave the x to the third alone. And then we'll take the derivative of the denominator. But when I take the derivative of the denominator, I'm going to have to use the chain rule. So the 2 will come out front. We'll leave the inside alone. Take 1 away from the exponent, and then I multiply by the derivative of the stuff inside the parentheses. But the stuff inside the parentheses is just going to be times 1. The derivative of 1x is 1. The derivative of positive 1 is 0. Does that sound good? So, okay. So that's going to be the numerator, and then just take the denominator. And I wrote the denominator. I don't know why I wrote that. We're not taking the derivative, just the denominator squared. I think I said that, maybe wrote it wrong. Hopefully I did. So just take the denominator. It was x plus 1 squared. Well, we're squaring that. So x plus 1 squared squared is just going to be x plus 1 raised to the 4th power. So what do we do at this point, ladies and gentlemen? So I've taken the derivative. What do we do with this? Because we're trying to find where it's increasing, where it's decreasing, maximums and minimums, concavity. We're trying to do all that stuff now. That's what we're trying to do. Canada, nice. Miss Stacy, I don't know if Miss Stacy's still out there. It's funny. Miss Stacy or Mr. Brown, Mr. Brown and Miss Stacy are both from Canada. That's funny. Maybe Mr. Brown is Miss Stacy's code name. Okay. So at this point, what we need to do to figure, we want to find critical points. We want to find critical numbers, or sometimes people call them critical points. Technically, it should be a critical number. And what we do is we figure out where the derivative equals 0 or where the derivative is undefined. We want to do those two things. You're going to have to help me with that last flag. It looks familiar, but not enough. So we want to figure out critical numbers. So to figure out where the derivative equals 0, to do that, we take the numerator and set it equal to 0 and solve. To figure out where the derivative is undefined, you do the same thing, but with the denominator. So take the denominator, set it equal to 0, and solve. Okay. So the denominator is easy. Macedonia. Okay, that sounds quite plausible. Thank you. That's cool. So if we take the denominator and set it equal to 0, that's x plus 1 to the, I'm going to do the easy part first. That's x plus 1 raised to the 4th. Or it means that x plus 1 would have to equal 0, or x would equal negative 1. But notice that's not a critical number because it's not in the domain. but I'm still going to use it for purposes of increasing and decreasing. Cool, Georgia. There's some, what was her name? Maya Chaya Bur. I forget. I don't know how to say her name. One of the famous women world champions was from Georgia. She was an interesting person. That's one of my, a little bit of my knowledge about Georgia comes from her. Reading about her. Okay, so that's not in the domain, but we'll still use it. The harder part is going to be setting the numerator equal to 0, and you really want to clean this up anyway. So let me take all this and clean it up. So I'm kind of jumping the gun a little bit. Let's clean this up. So what I'm going to do is I'm going to try to factor the numerator. So I'm going to clean it up first. I'm going to write this as 3x squared and take as many steps as you need. So I'm not doing much. I'm going to clean up the second term. It looks like I'll have a negative 2x to the third multiplied by x plus 1 all over x plus 1 raised to the 4th power. Louisiana, cool. Yeah, Maya, she was the woman world champion in chess. This was like in the 50s or 60s. This was I think it was in the 50s or 60s. Back in the maybe prior to that, back in the day. So we want to try to factor this, is what we're going to do. And I noticed a couple things in common. I've got x's to powers and x's to powers. And then I've got x plus 1 to powers, and I've got x plus 1 to powers. So I can factor some stuff out here. So notice I can't do anything with my constants. So I look at x squared and x to the third, and I pull out the smaller exponent. So I'm going to factor out an x squared. And then I do the same thing. I look at x plus 1 squared and x plus 1 to the first. Well, I pull out an x plus 1 to the first. So now what I think is, what would go back inside of those brackets so that when I distribute all of this stuff, I get back my original numerator? Well, I would need a 3 because my 3 is gone. I factored out an x plus 1 to the first, but I need an x plus 1 to the second. So I'm going to need an extra x plus 1. I would need my minus and my 2. And it looks like we would just need an x. And I think that would now be the numerator factored. And notice in the denominator, we've got x plus 1 raised to the 4th power. I can keep simplifying. I'm going to do 2 steps at once. Notice inside the brackets, which I'm going to write as parentheses, I'm going to have a 3x minus 2x, which is going to be an x. It looks like I'm going to be left with x plus 3, it looks like in the numerator. Notice I could cancel out one of my x plus 1s with one of my x plus 1s in the denominator. And I think Zambia, so cool. It's so still blows my mind. We've got people all over. So that looks to me like the first derivative. Tell me if I made a mistake, because it's certainly possible, because I'm halfway, well, not halfway, I'm talking as I'm doing this. So again, that's going to be the derivative. And notice again, that's what I said, right? There's like one calculus step, but then there's a lot of algebra simplifications to clean this up. Okay, so what the heck are we even doing? We set the denominator equal to 0, but now I would have to set the numerator equal to 0. So that means I'm taking x squared multiplied by x plus 3 and setting that equal to 0. That's going to give me x equals 0 and x equals negative 3. Those are going to be my critical numbers. Okay. So these are my critical numbers. So maximums, I should say local. Let me say local maximums, mins can only occur here. It can only happen at these two values, at 0 or negative 3. There doesn't have to be any maximums or minimums. If it happens, though, it happens at one of those two. Or potentially both. You can have local max at both points, local mins at both points, one of each. It doesn't matter. Okay, the way that we figured that out again is I like to make a little sign chart. So f prime, oh my gosh, this is a long problem. That's the problem with these. I like to make a little sign chart, and I use all of those values I found. So 0 was a critical number, -3 was a critical number. Now, we said that the derivative was undefined at -1. It's not a critical number, but include that when you start testing for intervals of increase and decrease. And I'm even going to put a little open circle there to kind of remind myself that it's undefined there. So this can't be, at -1, you can't have a local max or min there. Even if the function goes from increasing to decreasing or something, you couldn't have a local maximum because there's no point there, it's undefined. At this point, you just have to do a lot of test points, and I'm not going to do all of these because it's too long and it's very tedious. So you've got, let's see, 1, 2, 3, you've got 4 intervals. You've got to test points from, in this case, 4 intervals. And you can pick whatever number you want, just make sure it falls in that interval. So maybe I could use x equals -10. Then I've got to take a number between -3 and -1. Maybe I could test -2. And then something between -1 and 0. Maybe I would use -1/2. And then between something larger than 0. So maybe I'll use x equals 1. I don't know. Okay, so let me test a couple, see if we find anything. I'm going to test, let's test x equals -1/2. And again, all I'm doing is I'm plugging it back into the derivative. So I'm asking myself, is f prime positive or negative? So f prime at -1/2. So I'm plugging it back into my derivative. So I'm going to have -1/2 squared. And then I'm going to have, what was it, -1/2 plus 3. And then in the denominator, I'm going to have -1/2 plus 1 cubed. That's what I'm going to have. So all I'm really thinking about, is it greater than 0 or is it less than 0? Is it positive or negative? So -1 squared, that's going to be a positive number. -1 plus 3, that's going to be another positive number. -1/2 plus 1 to the third, that's another positive number. This is going to be a positive number. So I just plugged in -1/2. That means over this interval that my function is increasing. So I now know that f, the original function, is increasing on the interval from -1 to 0. I now know that that is happening. What if I take something larger than 0? So again, I said I was going to test something larger than that, and I plugged in 1. Notice in that case, I would get 1 squared, multiplied by 1 plus 3 over 1 plus 1 to the third. This again is going to be a positive. So I know that my function is still increasing past 0. So that means there's not going to be a local maximum or a local minimum at x equals 0. So maybe what the function is doing in this case, if I go back to my graph, it says the derivative is 0 for a second, but then it keeps going. And we said the derivative was 0. Where did this happen? At 0. Okay, so we can do that. So really I should tweak my graph a little bit more. I'm kind of updating it as I get more information. So we said that the derivative, we know that this is an asymptote. The derivative should equal 0, which means the graph kind of flattens out there for just a moment at x equals 0. But then it's got to still approach that asymptote. So my graph should look something like that. So I assume there should be a concavity change at x equals 0 is what should happen. And if not, we'll just see if my intuition's incorrect. So that would now be, and now you would have to go back and do the same thing. You would also have to test, so also test f prime, would we use -10, and also test f prime of -2. And just figure out where it's positive or negative. So again, does that help? And for concavity, you do the same thing, but on the second derivative. So do the same thing, but on the second derivative. Nope. We're done with that. Let's look at it where it's simplified. And especially if you're going to have to take, anytime you have to take multiple derivatives, once you take a derivative, clean it up. You have to clean it up, clean it up, clean it up, and then take the derivative. Always do the algebraic simplification first. Now, if we want to take a second derivative, before I do anything, I would distribute out the numerator and get x to the third plus 3x squared, and I would leave the denominator alone still. But the only reason why I'm multiplying out the numerator is because if I multiply out the numerator, again, I want to find the second derivative. That's where I'm going with this. If I multiply out the numerator, I don't have to use the product rule and the quotient rule. I know I've got to use the quotient rule because I got a fraction, right? There's nothing I can do about that. But if I leave the numerator as a product, I have to use the product rule within the quotient rule. And if I multiply it out, I don't have to do that. So to me, that would just be beneficial. It would just be easier for me. Okay, so now we just do the same thing. And maybe I will, maybe I won't. Tell me, should I go all the way through this one? You know what I'm saying, derivative. I'm typing too fast. Because from that, and again, you know, if the function, to find concavity, we're doing the same thing. We're going to figure out where the second derivative is equal to 0, where the second derivative is undefined. You feel okay with that? Just do the exact same thing. You'll find test points. Remember that -1 is not in the domain. So even if concavity changes at -1, you don't have an inflection point at -1 because there's no point at -1 on the graph. But otherwise, you're doing take the second derivative, where's the numerator 0, where's the denominator 0, put them on a number line, test points, and now if it's positive, it's concave up, and if it's negative, it's concave down. So I'm totally making up values here. I'm not saying these are correct at all. So let me even put that. These are, okay, I can't write. Not correct. But suppose these were, and I test some points and I figure out it's positive here, that means it's concave up. And suppose I figure out the second derivative is negative here, that means it's concave down. And that means that x equals -4 is an inflection point, you could say. Because it changes concavity. So you're just doing the same thing. So maybe I'll erase this so it doesn't look confusing. But that's all you're doing. And I like to write this too, just notation-wise. I like to write concave up, concave down, instead of, just so you don't get confused between increasing, decreasing. Make sure too that if you have to graph one of these, really keep things organized, because it's so easy for it all to start running together and you're trying to put these pictures together right in a good way. You're absolutely very welcome, Alexander. I'm glad, I hope it helped you, or at least got you quite a the ways there. Just be real, you know, be a good note taker and just be organized is all I would say, because it's easy for it to all start running together. And you've seen me too as I've gone through my picture. You probably would see me doing this. I would probably be working on my picture as I go, and sort of slightly modify it. Sometimes it feels a little overwhelming to try to put it all together at the end. But if I sort of tweak and update and tweak and update, by the time I get to the end, I'm pretty close. So, but again, it's a matter of personal choice. So whatever works for you. So, all right. So we've been on here for a good 90 minutes at this point. It's Sunday. I may hop off here soon and go through the dinner motions in not too long. So do all this stuff. I don't know. I guess the question is, I know clearly it was for hopefully at least a couple people, is this useful? Should I return? Not today, but in the future. And I know it's still early in the semester, so maybe people probably haven't got a ton of questions yet. But this is part of the reason why I wanted to start now, just kind of giving people a heads up that, hopefully we can have some, I can provide some consistency and help some people. If it gets really popular, which would be lovely, I would love for that to happen, maybe then I'll start breaking it down into a Calc 1 help session, Calc 2, algebra, trig, something like that, because if there's too many people, right, not everybody needs the same stuff. So, okay, all right, well, there's at least one person, so I'll come back. So thanks for the word, the little bit of encouragement. So, okay, I hope it did. Okay, you're always so nice, Federico. I think you would say that no matter what, but I appreciate it again from you as well. So, all right, I guess the last question too, is it useful to upload this note as a PDF? Would anyone use it? So I can really take, I can basically give you, I can upload this somewhere. It may be too all over the place where it's not useful. I could upload this somewhere. It feels like a hodgepodge, so it probably isn't useful. But if this was useful, I can put this on Google Drive and upload it somewhere. So just let me know. Put something in the comments. Last ask. Please thumbs up it, because that helps expose the video. YouTube likes that when you thumbs up it. Make a comment. Thanks or good job or whatever, that helps. And lastly, if you want to really help, again, Patreon's the place. And you know who I am. Again, no obligation. I do not care. So, all right, my friends. Are there new math concepts? Let's see, I'm not sure what that question was. Are there new concepts taught in school? Yeah, sure. Are they new math concepts? Would you be able to upload the algebra review session notes? Yeah, I think I have all those. I can upload those. Yeah, I can do that. Give me a few minutes, Federico. I'll go do that now. Yeah, I'll upload those. Give me a couple minutes. Everything is uploaded. Is going to be uploaded to Patreon. And you don't have to pay to get them. You can be a free. You can join for free. There's a free member option. So just sign up for the free member option if that's what you want to do. By all means, just sign up for the free member option, and that way you'll get a notification. So it's just a way to keep everything in one place, and it's also a way to, again, say thanks to people that are, helping a guy out on Patreon. So I'm trying to make it easy for them so that they don't have to dig around and look for it. So I will do that in just a minute. Federico, I will upload the algebra notes, so those will be out there soon. And otherwise, all right, if you're not in school, I hope you enjoy the last little bit of your break. If you're back in it, good luck. It's still kind of slow for now, at least where I'm at, but I think everybody will be in the thick of things pretty soon. So yeah, reach out, and I don't know. I'm going to keep trying to do something and be useful. Hopefully it'll happen. So if not, I'll just fade into the sunset. So all right, my friends, have a great day, a great evening, wherever you are in the world. Thanks for joining me. It's always a pleasure. I really do enjoy doing this, just meeting people. So it's I like being in here for 90 minutes. I'm kind of in my own little world, and I like it. You guys help do that for me. So anyways, thanks. Have a great day, and I will see you in the future. Peace out.